All right, Chapter 3, Problem 27. We throw a ball horizontally from the top of a 60-meter building and it lands 100 meters away. All right, so we're up here on a building. We throw the ball straight horizontally and it lands, boom, over here, right? That's 100 meters. The building is 60 meters tall. And so the question is, how long was the ball in the air? Well, remember from lecture, these two components are independent, right? What's happening in X and what's happening in Y are two different problems. So the question, how long was the ball in the air? The X component doesn't tell us anything at all about that, right? Because in the X direction, it's just going along in X at whatever velocity we threw it at. Why? Because of this sentence right here, ignore air resistance. So there is no force along X. Since there's no force along X, there's no acceleration along X, it keeps going the same velocity the whole time. That means Y. Y is the direction of interest in determining how long is the ball in the air, right? All right, so what's going on in Y? What's up in Y? So what's the equation for Y? Is 1/2 AT squared, right, plus V naught Y T plus Y naught. Okay, now when we start the problem, what is Y naught, right? Y naught is 60 meters. What is the initial velocity in Y? Well, we throw the ball horizontally, so the initial velocity in Y is also zero. Is zero. The initial velocity in Y is zero. What is the acceleration? We're taking up to be the positive direction, so the acceleration is due to gravity is minus 9.8 meters per second squared, right? All right, now when the ball hits the ground, right, we're asked how long is the ball in the air? Well, the ball is no longer in the air when the ball hits the ground. So when the ball hits the ground, what is our position? It's Y equals 0. Y equals 0, right? Equals minus 4.9 meters per second squared times time squared. All right, V naught was 0, so that component is gone, plus 60 meters. This is the equation we have to solve. What we get to is T squared. T squared is 60 meters, well, 60 seconds squared, right? 60 divided by 4.9. Well, the algebra works out. Okay, so how did that work? I took this, right, and added 4.9 meters per second squared T squared to both sides, so that I got 4.9 meters per second T squared on this side and had just 60 meters on that side. And then I divided by the 4.9 meters per second squared, so that I'm left with just T squared, right? Okay. And this gives us T equals, all right, let's turn to Excel. T equals 60 divided by square root of 60 divided by 4.9. Right? And there's 4.9 because it's 1/2 of 9.8, right? All right, so we get 3.5 seconds. T equals 3.5 seconds. Excellent. So that's the answer to part A, right? Go up here, put in a little part A. All right, so now part B is what must have been the initial horizontal component of the velocity. Okay, initial horizontal component of the velocity. Now, what do we know about the velocity in x? Right? We start off knowing nothing, but we do have two constraints now. We now know that when it hits the ground, the time is 3.5 seconds. And we also know that when it hits the ground, we are 100 meters away from the building in x. Right? So if we write down the position in x, x equals v naught xt. Well, all right, let me back up. 1/2 ax t squared, right? Plus v naught x t plus x naught. All right, so as we said before, ax, the acceleration x, is 0. We don't know v naught x yet. We do know that x naught is 0 because we can choose that, right? We can choose the building as our starting point. All right, and we know when we hit the ground, t is 3.5 seconds, and we know when we hit the ground, x is 100 meters. That means the only thing we don't know in this equation is v naught x, right? So it simplifies down to, putting in the zeros, x equals v naught x t, right? So v naught x equals x over t equals 100 meters divided by 3.5 seconds equals 100 meters divided by 3.5 seconds, 29 meters per second. 29 meters per second. That's our initial velocity in x, 29 meters per second. All right, that's the answer to part B. Part C, what is the vertical component of velocity just before the ball hits the ground? All right, just before the ball hits the ground. So part C. Now we're back to the y-axis, right? Vy is acceleration in y times time plus the initial velocity in y. Well, we've already said that v naught y is 0, and we've said that the initial acceleration in y, I didn't label it as such up above, the initial acceleration is minus 9.8 meters per second squared, right? And we know when we hit the ground, again, that we know that t is 3.5 seconds. So this gives us, as we hit the ground, right, just as we hit the ground, Vy is minus 9.8 meters per second squared times the time, 3.5 seconds, right, plus the initial velocity, which is 0. So we're looking at it minus 9.8 times 3.5 equals minus 9.8 times 3.5 equals minus 34 meters per second. Minus 34 meters per second. That's our velocity in y just as we hit the ground. Okay. Part D, what is the velocity, including both the horizontal and vertical components of the ball, just before it hits the ground? All right. Part D. So now, the velocity as a vector, because we're including both components, is the velocity in x, which is 29 meters per second, right? 29 meters per second in the x direction, plus minus 34 meters per second in the j direction. All right, so I'll take out the plus. All right, so 29 meters per second in the I direction, minus 34 meters per second in the j direction. What is the magnitude, right? Magnitude of V is just going to be the square root (29 squared plus 34 squared). This is meters per second. All right, square root of 29 squared plus 34 squared is 45 meters per second. Okay, so we got a velocity of 45 meters per second. And the angle, if you think about it, the angle is we're going 29. Oh, let me restart that. Let's see if I can draw a little bit better. 29 meters per second that way and 34 meters per second that way, right? So we're after this angle. And so we have theta equals the inverse tangent of 29 divided by minus 34. Tan 29 divided by minus 34. Okay. Convert that to degrees at minus 40 degrees. Make sure I got the significant. Yep, minus 40 degrees. So, that means the vector would look like this. It would be 45 meters per second long, right? And the angle is minus 40 degrees or 40 degrees below the horizontal. So the way I've drawn it, I need to draw that as a plus 40 degrees, right? 40 degrees below the horizontal. And that's it for part D. And we're done with this problem.